Common types of external loads include the following: concentrated forces, which are idealized as acting at a single point; concentrated moments. These moments are assumed to be acting at a single point and are generally categorized as either bending moments or torsional moments. Distributed forces. These forces are distributed over a certain length of a structural member. Just as an example, we see different types of external loads acting on this cantilevered beam. The 10 kip load and 8 kip load acting downward act at a single point, so those are concentrated forces. This concentrated moment of 40 kip feet falls into this category, concentrated moments. And then this distributed load, this has a load intensity of 2 kip per foot. That's a force per unit length. Structural supports keep a body in place. The most common types of supports are shown in this table. For each support shown, the number and type of support reactions are indicated. So it's important to study table 1-1 and to start memorizing all these different types of supports and connections. To summarize them, we have cable supports, 1 unknown support reaction; roller support, 1 unknown support reaction; smooth support, 1 unknown; a journal bearing, 1 unknown, very similar to a roller support, as you can see; an external pin, 2 unknowns; an internal pin, 2 unknowns; a fixed or rigid support, the most restrictive kind; 2 forces and a couple moment reaction; and a thrust bearing, which is very similar to a pin, 2 unknown force reactions. The vast majority of problems in mechanics of materials require 1 or more free body diagrams, or FBDs, to be drawn as part of the solution. By definition, as we learned in statics, a free body diagram shows a structural member isolated or freed from its surroundings. The diagram shows the outline of the member, all forces and or moments acting on the member, and the relevant geometric dimensions and directions, such as directions of vectors. So consider this example, which shows the given problem diagram on the left and provides the FBD on the right of the isolated structural member. And we have an engine hanging from this beam. This beam is being supported by a pin connection at A, and we have this connecting rod here supported through this connection here, a pin connection and a pin connection here. We have A sub X and A sub Y, these support reactions at A. And since we have this connecting rod here, a 2-force member, we have this force F sub CD acting at this point on the beam. We have all the dimensions labeled. The direction of this force vector is labeled through the use of a slope triangle. We have the weight of the engine, which is an applied force. So this is a complete and proper free body diagram of the beam AECB. As discussed thoroughly in statics, equilibrium implies a balance of forces and moments. Recall the vector equations of equilibrium. These state that summation F equals ma, that must equal 0. And summation m sub o, the net moment about some point O, equals I sub o alpha, that must be equal to 0. So the equation for forces, the first one, states that the net force on the body is 0 and ensures that the body is not accelerating translationally. The equation for a moment one states that the net moment on the body is 0 and ensures that the body is not accelerating rotationally. For a general 3-dimensional scenario, the 2 vector equations we just mentioned contain within them 6 independent scalar equations of equilibrium, and they state that the net force in either the x, y, or z direction must equal 0, and the net moment about any of the x, y, or z axes must also equal 0. For a simpler 2-dimensional scenario that is a case of coplanar loads, these reduce to 3 scalar equations of equilibrium, where the net force in the x direction must equal 0, the net force in the y direction must equal 0, and the net moment about any point must also equal 0. It is often necessary to determine the internal loads acting at a specific point in a structural member. To do so, the method of sections is used, in which an imaginary cut or section is made on the body at a point of interest. And the resultant internal force and resultant internal moment can be determined using the equations of equilibrium. This resultant internal force and resultant internal moment can be resolved into components that act perpendicular and parallel to the sectioned plane. Normal force, this is a force vector that is perpendicular to the sectioned plane. Shear force V is a force vector parallel to the sectioned plane. So the bending moment is uppercase M. This is a moment vector that is parallel to the sectioned plane and causes bending of the member. And lastly, torsional moment, or simply torque, uppercase T, is this moment vector perpendicular to the sectioned plane that causes twisting along the longitudinal axis of the member. But for a simpler 2-dimensional scenario that is a case of coplanar loads, all forces and moment curls act within a single plane, such as the XY plane. Internal loads must be properly reported as either positive or negative. The positive or negative sign on an internal load provides critical information regarding how the member deforms as a result of that load. Illustrated here is the sign convention for deformation due to internal loads. An internal normal force N is deemed positive if it causes tension and negative if it causes compression of the member. An internal shear force, shown here, is deemed positive if it causes the segment to tend to rotate in a clockwise manner and negative otherwise. An internal bending moment M is deemed positive if it tends to bend the segment in a concave upward manner and negative otherwise.